Okay, so here we have a problem where we deposit $4,000 into a savings account earning 10% annual interest, compounded continuously. To pay for all your music downloads, each year you withdraw $900 in a continuous way. A of T represents the amount of money in your savings account T years after your initial deposit. We want to write a differential equation model for the time rate of change of money in the account. We also want to state the initial condition here. So, part A, we're going to create a differential equation model, and it's partly already written for us. dA over dt, and that will equal, when you read this, we know it's a 10% annual interest, which essentially means we will have 0.10 times the original amount, or the amount. And then we also know that $900 is taken out continuously. So, right here, we have our differential equation. And we're almost good. Oh, we also need an initial condition. And our initial condition, we know to start with, was that we originally have $4,000, right? When we first put it in. And that's part A, finding a differential equation model with our initial condition. And at this point, we can actually solve the initial value problem. The way I'm going to do it is integrating factors, and I'm going to actually change dA dt into a prime, just because it's easier for me to look at that way. And I'm also going to move the 0.10a to the left side as well and set that equal to negative 900. And in this form, it makes it easier for me to see that I have a first order linear equation, and I can use integrating factors to solve this. And the integrating factor is going to be the e to the integral of what's in front of the a term, and that is negative 0.1, which I'm actually just going to write as a 1 over 10. And then in terms of t, integrating that, we get e to the negative t over 10. And that is our integrating factor. So what we do, if you remember solving with an integrating factor, we multiply that to the whole differential equation. So e to the negative t over 10 times a prime minus 0.10 e to the negative t over 10 times a, which is equal to negative 900 e to the negative t over 10. And then what's nice about that is that we can rewrite this as the product rule. So the derivative of our integrating factor, e to the negative t over 10 times a. And that is equal to negative 900 e to the negative t over 10. 10. And I'm going to write dt because I'm going to integrate in a second. Just to double check, notice if you took the derivative of this, you would get the above step here, right, using the product rule. So that's one reason why we like the integrating factor. It makes that nice. And now we can integrate both sides. And once we integrate, the integral of a derivative essentially cancels it out. So we're left with e to the negative t over 10 times a being equal to, when we take the integral, it's just essentially itself, e to the negative t over 10, but we have to take into account that fractional part, so we end up with 9,000 e to the negative t over 10. Again, if you took the derivative of this, it's always a good check. When you take the derivative of e to the negative t over 10, you get itself times the derivative of negative t over 10, which is negative 1/10, and you would end up with negative 900 there. So that checks out. And then, of course, do not forget our plus c at the end there. And now, use a different color. We have, I want to divide to get a by itself, the whole equation by e to the negative t over 10. And when we do that, we get a of t is equal to, this cancels out, 9,000 plus c, constant, e to the t over 10. And then, of course, remember our initial condition of $4,000 when t equals 0. We can then get what c is. 9,000 plus c, and this is just, e to the 0 is just going to be 1, so we're just going to have, of course I made a little typo here, so let me write what that's supposed to be. $4,000 equal to 9,000 plus c times e to the 0, which is just 1, so you have 4,000 equals 9,000 plus c. Solving for c, subtracting 9,000 from both sides, you get negative 5,000. And so our wonderful solution looks like 9,000 minus 5,000 e to the t over 10. And I'm going to box that, because that pretty much we can use for however long we want to plug in any value of time to see how much money we will have left. And the last part of this problem is to figure out when we run out of money. And when that happens is when the amount at some time will be equal to $0. Right? So all we need to do is solve this equation. When you have 0 money, 9,000 minus 5,000 e to the t over 10. I will move this to the other side to get 5,000 e to the t over 10 being equal to 9,000. Dividing both sides by 5,000, and I get e to the t over 10 being equal to, when you simplify this, you will, oops, I forgot a 0. You get 9 over 5. We want to solve for t. If we take the natural log of both sides. That's nice because then we can make use of some properties there to get t over 10 being equal to the natural log of 9/5. And I'm going to draw a little arrow here because I'm running out of space on this bottom. I don't want to scroll down. Multiplying both sides by 10 to get t by itself, we just get t will equal 10 times the natural log of 9/5. And that is our answer, except for the fact that we don't usually say time in terms of 10 ln 9/5. We say it as a number. So when you plug that into your calculator, it's going to give you a number, and that number is about 5.9 years. Hope that made sense.